Now, we've already talked about the dot product, but suppose there's another type of product that we could think of, which is called the cross product. If we have a u and a v, which are vectors like this, and we wanted to create another vector, w, such that w was perpendicular to u and was perpendicular to v. How would we do this? Well, we would know that u dot v dot w should be equal to 0, and v dot w should also be equal to 0. Well, this actually has a whole family of solutions, one of which would be that w would be equal to u2 v3 minus v3 u2 u3 v1 minus u1 v3 and then u1 v2 minus u2 v1. And you can check it for yourself. Do vector w dot vector v, you'll find it's equal to 0, and vice versa. If you do vector w dot vector u, you'll also get 0. This w, this vector w, is called the cross product of u and v, and it is written as u cross v is the cross product. Now, this seems very complicated, but there's actually a simpler way of computing the cross products than solving the above system or memorizing this giant formula. And it uses determinants. The cross product is also known as the vector product because the cross product gives you a vector, just like how the inner product or the dot product was known as the scalar product because it gave you back a scalar. So let's recall what determinants are. Determinants are given by matrices. So if we have a 2 by 2 matrix, then we have A, B, C, D, and the determinant is just A times D minus B times C. And a 3 by 3 matrix is going to have the determinant of A1 times the determinant of this box minus A2 times the determinant of, if we cross these out, this box plus the determinant of A3 times the determinant of, cross out these, and this box. B1, B2, C1, C2. Which, if you simplify this, is going to be A1 times B2, C3 minus B3, C2 minus A2 times B1, C3 minus B3, C1 plus A3 times B1, C2 minus B2, C1. Now, these 2's and 3's, this pattern should seem similar to how we found this W. 2 3's, 2's and 3's, 3's and 2's, 3 1, 1 3, 1 2, 2 1. Look at how that all matches up. So, we can calculate the cross product in a much nicer way by saying U cross V will just be as if we created this matrix with I hat, V hat, J hat, and K hat as the top row, and then U1, U2, U3, V1, V2, V3, and we took the determinant. Because if we have I hat of the determinant of u2, u3, v2, v3 minus j hat of u1, u3, v1, v3, and then add the k hat of u1, u2, v1, v2, and we did the determinant of each one, you'll see that it is going to be identically the formula we had originally for this w, this vector w. And remember, this minus sign in calculating the determinant is crucial. A lot of people forget that there's this minus sign here. And that's just how determinants are calculated. You need this minus a2, not just plus a2. As a note, where dot products can be easily generalized to two vectors of the same dimension, any two vectors of any dimension, the cross product only makes sense in three-dimensional space. Seeing as how we're using I, j's, and k's, which is our standard vectors for three-dimensional space, we should stick with cross products of three-dimensional space. Let's do an example with u, the vector u being 1, 3, negative 2, and the vector v being 2, 4, 6. U cross v, in order to calculate this, we'd create our matrix. I hat, j hat, k hat, and then the vectors. Then we use our formula to be able to calculate determinants and say we have I hat times the determinant of 3, negative 2, 4, 6 minus j hat times the determinant of 1, negative 2, 2, 6 plus k hat times the determinant of 1, 3, 2, 4. All right, so what do we do here? We calculate the determinant using AD minus BC. We have 18 minus 8, so we get 24. 18 minus 8, which is 26. So we get 26 I hat minus j hat, which the determinant of this is 6 minus negative 4, or 10. So we get a minus 10 j hat. And then we get k hat times the determinant of this. We get 4 minus 6, negative 2, so minus 2 k hat. And remembering what I hat, j hat, and k hat are, this is just the vector 26, negative 10, negative 2. And this would be the cross product of u and v. And if we do the dot product between either of these, we are going to get 0.